still on the part of this relativistic kinematics, we can talk one experiment. This experiment is probably, it's called Compton scattering.
Yeah, Compton scattering, yeah.
This is one of the perfect example to understand this relativistic kinematics and particle physics. This is actually one of the first problem when physicists try to solve. They first time incorporate this idea of particle nature to solve this problem in terms of using the quantum mechanics and relativity. So let's first try to focus on this problem, and then when we at some point reach, ultimate target will be to calculate the Compton wavelength shift or Compton wavelength, and then when we calculate the Compton wavelength, from the Compton wavelength we try to understand how we define these fundamental units. So I think it will be more easier way, just like last time. Last time when we talk about this unit, I think I make one mistake. I think I say the unit of H is joule per second, but I do not joule per, it will joule times second.
Joule second.
Because E is equals to H nu. So this is
H
1
nu,
over
yeah.
time. So it will be joule times second. Yeah, so ultimately our main goal is to first, let's try to do this Compton scattering. Okay, and then we first try to calculate something called Compton wavelength or Compton wavelength shift. That will be, we'll see something with something, and this will be some, it will be some kind of quantity which will be first here in the dimension of length because it is a wavelength. So when we try to calculate this length, and then we'll see how these fundamental units can one think in a better way. I mean, just I can say something better than we'll do something, and then we try to figure out from here to the point what we are talking about. Okay, so one thing before Compton scattering, there is also one more scattering was physically explained. It is called Thomson scattering.
This with the alpha particle, right?
It is not really with alpha particle. It's also with let's first focus on this one. Then we'll come back to here, and then finally we will reach at some point. Then we'll try to see the full picture how it's work. So we'll come back to Compton scattering in a bit later. So I just for a second I remove this part. So initially, before the quantum mechanics come into picture, it was considered that light is a kind of wave. So let's consider it as a kind of collimated beam or beam of photons, which is like a low energy. It's a low energy compared to the electron bound state in hydrogen atom. If I consider hydrogen atom bound state, so the energy is of the order of 10 eV, which is exactly like 13.6 eV. So EV is 1 EV is, so do you know the relation between them, this EV and joule?
1.6 10 power minus 19 joules.
Exactly. Yeah. So now in high energy physics we are mostly focusing on the unit of EV instead of joule, because joule is like a classical SI unit. Joule basically called SI unit. So instead of considering joule, so now we are mostly talking about electron volt unit. And so in electron volt, either you can say electron volt or mega electron volt or GeV or TeV. So this kind of energy unit we will basically consider now instead of considering joule. Okay, so now when we talk about the Thomson scattering, so we consider a kind of beam of photon is of the order of less than 13.6 eV, which is the bound state of an electron in hydrogen atom. Then what we consider, let's consider there is one electron is at rest. So it is electron in the hydrogen atom bound state. Now when a photon, now or kind of beam, I'm calling it a beam of photon. So now I consider it as a wave now. So it is a classical picture. It's fall into this electron. So I consider this is photon. And here, when I considering the wave, so that means it had some wavelength and frequency. So if I last to complete the picture, so I consider EF now, because this nu is I put it for photon just to gamma. So I consider this F is a frequency, and lambda, this is the wavelength, and product of these two I define as a c, the speed of light. So this is kind of standard unit. I will just put it here so that I can use it later. Now when this photon falls into this electron, which is in the bound state, and this photon energy, again I just let me repeat, is less than 10 eV. So this photon had not have enough energy to emit this electron from the hydrogen atom outside cell, or if because electron energy is more than the energy of this photon, and it's a wave. Now what will happen when this electron absorb this energy from the photon? It start to accelerate because it's getting some energy. And according to the formulation of electrodynamics, that when any charged particle absorbs some energy, it start to oscillate or accelerate. So this electron will be accelerate, and then it will emit some further photon.
Okay.
So again, this is a classical picture. So this picture is not quite. So here I consider photon as a wave, who is having wave. So let's consider the photon have a wavelength lambda. It falls into the electron. So this electron absorbs some energy and it starts to accelerate. So when it's accelerate, and we know when any charged particle accelerate, it's emit further photon. Now here, whatever be the amount of energy of this emitted photon, the outgoing photon, this is supposed to have the same energy. Because this electron, it was in the bound state, it just absorbs the energy, oscillate, and just emit the photon. So here, the wavelength of this outgoing photon will also be lambda.
Yes.
So this kind of scenario in classical picture we call it Compton scattering.
Okay.
And if you want to do some mathematics, suppose you want to calculate what is the intensity of this photon which is fall into it and is basically generate the other photons, or if you want to calculate something called d sigma of d omega, this is called cross section, and omega is called solid angle. So what we basically do, so it's not only suppose this is more photon, is because it's a bunch of photon, because I consider it's a wave. So when it's a wave, it's a bunch of photon. So a bunch of photons are incident on this. So I can consider, so this is the axis, this is the photon is falling into this electron along this direction. With respect to this, we can define a small angle here, and with that we can define one solid angle. And then we can calculate this d sigma over d omega. This is called cross section. And this is solid angle, which is nothing but the A. So one can do some classical calculation, and then they can calculate this cross section per unit solid angle. And then we can find out some, if need, we can do the calculation later, but this is not important for this picture. Just to complete the story, let me write down the formula what we can use. This is one of the homework I am planning to give you, and I will give some hint how to calculate. So for that's why I just want to write down the formula for a moment. Okay. Yeah. So then one can calculate this. I'll give you later some hint how to calculate this, because this is something kind of important one, because this is a place where it's basically help one to think to move the picture from classical to quantum mechanics, and it's very easy to do the calculation. So this theta is the angle with respect to of, if I consider one, because the photon is collimated photon, so this photon will be emitted like again in a collimated way. So I can define some angle theta here. So then one can calculate this cross-sectional area.
Okay.
So this is a picture of the Compton scattering, and now let's try to move the picture in other way around, because this is not something what we are interested. That we are interested to see the picture in terms of quantum mechanical way. So to do that, let's consider instead of this photon, what we are talking about here, we consider one photon now as a parcel. So here I consider this photon instead of the wave, I consider it a particle against beam, and then there is one electron which is that this is fall into the, so this is electron. Now what a difference between this one and the previous one? The previous when I discuss about the Thomson scattering, I consider the incident photon have energy less than the bound state of this hydrogen atom electron. Now I consider this is kind of X-ray, and this energy can be ranged up to 100 eV to 1000 kilo electron volt. So this is more energetic photon. So when this more energetic photon is falls into this electron, which having higher energy now, then this photon or this light beam has enough energy that this it can move, it can take this electron out from the bounds because it has enough energy. So now let's consider this is the axis of the incident photon. This electron is recoil, or it's come out of this from the bound state, and this photon will be just scattered from here. So this is my incident photon. Let's write and this is outgoing photon. So see, let's try to understand what the difference in the previous one. So previous one, as I said, one thing is that it was low energy.
The energy is lesser than the bound state, and then here the energy is higher than the bound state.
Yeah, so in the previous case,
yeah.
So the previous case, whatever the photon was coming out, it is just because of radiation, because the electron had accelerated, so it's radiate. Now, do you think in this case, what will be happen? That will be the energy of the incident photon and energy of the outgoing photon will be same, or it could be different?
No, it will be different, because additional energy must be going to the electron that is being kicked off of the orbit.
Yes, exactly. So now, so that is a kind of, so when they try to do this kind of expositor thought experiment, one was thinking how one can, because this is a, I think it is one of the long time ongoing problem apart from the photoelectric effect what Einstein solved by his quantum mechanical approach. Not solve, but give some hint how to solve it. So this is also one of the problem when Compton do this experiment, and when he measured the wavelength between the incident photon and outgoing photon, he said he observed that these are not identical, and then he tried to understand how this problem happens. Because if I consider wave approach, when they consider wave approach, this problem cannot be solved. So now here, so let's try to calculate. So I define the energy of the incident photon as EI and momentum of the incident photon as EI. And then for outgoing photon, is final and momentum also final. And this one, so this electron was initially at rest, but now after the collision or after the scattering, this electron had energy and momentum. But here initially this electron had some rest because this electron was at rest, so it had rest mass, and momentum was zero. So our main way now, we want to calculate what amount of wavelength can see. So before doing the calculation mathematically using the 4 vector, why I'm doing this one, because this is the one problem here I want to introduce, because if you know the 4 vector approach, so I can just start from there, and if you don't know, we can just give a kind of small reminder for ourselves what kind of mathematical abracadabra one can do with the 4 vector. And then we can calculate the final one. What do we want to calculate? The wavelength of the final state, final photon minus wavelength of the initial photon. Either it is, we will check either it is 0 or it is non-zero. Okay. So now let me ask you. So what up? So I guess you know about the 4 vector mathematical formula.
Yes, I know about the 4 vector, but you mentioned like additional points, like some small reminder of like where can it be used, how can that be very helpful.
Okay, so let's probably we can just give a very short discussion on the 4 vector, because this is something we need several times now. Like the problem you was just discussing few minutes ago regarding the photon, so you are thinking in terms of like energy and momentum. I mean, individually calculating distance, times and all. So instead of doing that also, we can use a 4 vector approach, and that's really helpful to do some calculation easily. So let's, okay, so this is our, at least for like 1 hour, after 1 hour, we will try to find out the answer of this question. Okay. So before that, let then have a look a little, because this will be helpful, because even when we later doing this Feynman calculation approach for Feynman diagram and all these things, then also we'll try to use this 4 vector approach for solving some problem. So it will be really helpful. Even you want to solve some problem in any way, this 4 vector will be really helpful. Okay. So for a moment, I just erase this part. So this is the picture what you just remember, because probably if needed we can draw it 1 second later. So now we will do this relativistic . So just a few kind of thing which we used like a standard notation kind of thing whenever we consider photon. So like, okay, one thing first, let me write down the most famous equation by the great Einstein. Okay, so here this m, like last time also when you just doing some kind of brush up, we said this m should be like rest mass. So this p will be momentum.
So rest mass is the mass that is same in any frame of reference.
It will be any frame of reference, like but it will be like a frame of reference of that. Like if I want to calculate the mass of or like muon. So suppose this, like if I want to calculate the mass of this object, so it will be like, it's supposed to be, if it is rest, what will be the amount of energy? If it is not moving, it is at rest, then what will be the amount of energy? That energy will be corresponding to this mc square. We will used very often to, that's actually will help us also to define the fundamental units also. We'll come back to this later, because that is the final question what we want to discuss to get these fundamental units. So before that, let's do some more non-relativistic stuff just to keep it on the board. So if I consider kinetic energy, so all this thing you know, but just I want to keep it on the board. So whenever we need, we can use it. So we can write it as half mv square. Again, this v is like a rest mass. And momentum we can define is mv. So can you tell me what kind of relation one can make between energy? So how I can write a relation between energy and momentum? So if we just do this kind of small mathematical abracadabra, you just put this instead of p by m. So you can get one relation. Energy to be half m time p square over m square, you get p square over twice m. So this is also one of the relation I just want to keep it on board. Whenever we needed the relation between energy and momentum with mass, we can use E equals to p square by twice m. So this is also one of the relation we'll get consider. Now, if I consider photon, so this is just as any kind of particle which has a mass, so classical particle. Now, whenever we come to the picture of photon, as I mentioned last time, photon is like a peculiar particle, which we know it doesn't have a rest mass. So for that case, if we want to calculate the energy, so it will be, so this rest mass will be 0 because photon doesn't have any rest mass, so it will be like Pc. So till now we don't reach up to our fundamental unit. Later when we reach to the fundamental unit, we just put C equals to 1, so energy and momentum will be identical. So this is some of the things what we can get from the non-relativistic cases where we know the energy and momentum. Also, if we think in terms of Einstein formalism, we can get the relation between energy and momentum. Now, one more thing before to go to this 4-vector one, let me define. Like last time we were talking about the space-time interval. So now usually in some of the book or some of the notation, sometimes they use like this one, which is called covariant. It's not invariant, it's covariant. That's the kind of naming of this notation. Some of them they use this notation. Just for simplification of our discussion, we just simply use capital. So this capital one will be represent the 4-vector. So if I write capital P, this is a 4-vector momentum. If I write small p like this way, it will be like the magnitude of the vector, or if I can use the vector notation. Just for keep the discussion simple. But one can easily use x mu. So this will be the identical one. Or if I take capital P, so one can use P mu. Okay. So now, if I want to define this position,
one question.
Yeah.
Sorry, one question.
Yes. Please.
So sometimes I'm seeing like the mu goes upwards, superscript, or mu is down, subscript. So is it like a mu downwards, the subscript is equal to like the first vector and then the second vector are all negative.
Yeah. So the notation is basically used in this way. Suppose you want to calculate x mu of
times
x mu. So this is what we call inner vector or inner product. So in some of the cases, like whenever we define, I can define this vector like Ct. So the zeroth component I define as a time, and the position, or sorry, and that I use the vector r. So this is a 3-component vector x1, x2, and one can write this one like this also. I think some cases they just use the first term. If I'm not wrong, in some of the, I think different book and different notation. In some of the cases they use this one negative, or some cases they use this one
minus r vector.
Like minus r, sorry, not the zeroth component but minus r. So in some of the cases they use, it is a positive one, it is a negative one, and so this is kind of depending on the notation or convention whatever they used. So I don't want to reach into this kind of not to confuse us. But yeah, this is if it is a covariant, it's a contravariant. So this kind of thing we
should multiply by gamma on the front, gamma times CT gamma r.
This one here.
Gamma we can ignore. For both.
No.
X mu is equal to
here
gamma
I can just
CT
define as a, no, I mean here we don't need, I did not make any transformation.
Okay.
I just write down whatever the space is. Okay. So for me, I just, to make the life simpler, I just use CT and R. Now one thing what I want to, so just to make it clarify, so for me this is CT and my 3 vector x, y, z. So this is a component of this 3 vector. Now let's do a little bit of mathematical calculus just to complete a story. When you do this Lorentz transformation, as a last class discussed what the difference between Lorentz transformation and Galilean transformation. So Galilean transformation is a classical one, and also when the particle moving with the speed close to the speed of light, then we use the Galilean transformation. And then under Galilean transformation, so if I want to, so this instead of writing CT, I just to make it, I write like zeroth component here. So this zeroth component and then x, y, z. So this zeroth component, when you do transfer, so if I consider the transformation is along one direction, not like, so this y and z or x2, y3, they are not affected, only the thing these two. So now just to make this calculation more simpler, I consider the particle is moving in one direction. So whatever the transformation happen, it will be only on particular one direction where the particle is moving. So this is a thing also is important. Why I'm saying this one, because suppose you are doing some experiment, like something called fixed target experiment. Suppose there is a target which is at rest, and there is one beam which is coming and collide. So in these cases, whenever we discuss kinematics of or dynamics of this kind of experiment, we mostly focusing on, or we try to understand all the physics along the direction of the beam. So whenever we do any kind of calculation, we always take this as a reference frame. So with this direction of motion, we want to calculate how the other physical quantity make effect before and after the collision. Okay, so when I want to make this relation between them, so it will be x1, I mean the zeroth component, minus beta times x0 over square root of 1 minus b square by c square, where b is b over c, and this quantity we can write gamma So this is how your component will be transferred. So we can make this expression more simpler. We can write gamma x1 minus beta x0. So this is how the Lorentz transformation happens. So whenever we are even like when we do this later when you do the Feynman formalism to calculate the final scattering cross section, then this will help us. So that's why I just note down here. And then also you can calculate how these two quantities, like how your x1 prime will be with the same and the same formalism. You can calculate how the x1 will be noted. And last time I discussed one thing.
So one quick question.
Yeah.
So the prime is a moving frame of reference.
It is moving frame of reference. Yeah. So when I consider this x0 or x1, x2, x3 is in my rest frame of reference, and it will be go like x0 prime, x1 prime, x2 prime, x3 prime. So this is under the Lorentz transform.
So the moving frame of reference, the length is shorter. So x1 minus beta x naught. No. The time is shorter. Sorry.
Yeah, time is dilated. Length will be contracted.
Time is dilated.
Yeah. So last time we discussed one more thing. I mean, just why I'm saying this one, because this kind of thing is a fundamental one. So saying more than one time will be always better, so that this thing will be in our mind forever. So now I discuss one more thing. So this x is my 4 vector once again. I use this notation on, and so this is kind of inner product of 2 4 vector, and the notation I will use, it will be x naught square. So this is a 0th component square minus, sorry, I should use a small letter. So this is a 0th component minus the vector. So this is scalar component minus vector component. So this is the way I will define my 4 vector inner product. So this thing also you can write like x0 square minus r1 dot r2. So r1 is the vector for the first for this one, r2 is for this vector. So if I want to write down this one, let's just to make it clear, I can write like this one as x0 r1 vector. This will be x0, I just again take x0 r2 vector. Just to clarify, because I use r1 r2 because I just want to see this how the dot product happened here. So when we do the inner product between 2 vector 4 vector, so this will the dot. So this is a scalar quantity, so you can just simply multiply. So but in case of vector, you cannot simply multiply. You have to do the like dot product. So here, so this quantity, whatever we want to calculate, so this quantity will basically give us some number, because this is a scalar quantity, and dot product of two vector is also scalar. So this will be give you some number, and this quantity last time we discussed as our space-time interval.
Okay.
What is meant by space-time interval is like suppose you have, so there is one event happened here, I call as a E1, and this event I basically define with this vector. So these two events happen at the same time, so I use a time as the same, and other one happen here, E2, at the same time but at different position. And when you try to calculate the space-time interval between these two events, that basically give you the inner product. We call this like inner product. and this quantity will be remain invariant under Lorentz transformation. Like last time we discussed in the class that our space can be, time can be diluted, length can be contracted, but this space-time interval will be remain invariant under Lorentz transformation. Okay. So one more thing I just want to clarify here. So when I consider,
but this is a homework that I can take and see like whether to confirm if that one is really true. Like if I do the Lorentz transformation of this E1, E2, and then do this inner product of x dot x in the x prime dot x prime, and then make sure like that is the output is still the x square minus.
Exactly, this is one of the homework I wanted to give you. So you want to first you want to calculate this one, like here I give you some example. So where you can calculate the inner product of two factor, and you know that's why I just mentioning here. You have two event here, and you do the Lorentz transformation between them, calculate the space-time interval between, and then check either before the Lorentz transformation and after the Lorentz transformation either they are identical or not. If it is identical, that means it is Lorentz invariant, and it should be. Otherwise, the concept of whole relativity will be spoiled down. The whole work of Einstein, Minkowski, and all this will be go up to the garbage, because that's one of the important quantity what they defined. That your length can be contracted, time can be dilated, but your space-time interval will remain invariant. Okay. So this is about the space and time. Now we can go the same. We can draw the same picture in terms of momentum. So now again we want to define the force momentum. So I use a capital P. This is the notation for me to define the force momentum. And last time, if you remember, I was start to discuss one thing, how we define momentum. So I not repeat once again, but just to write down delta T tends to 0. There should be a mass term, and then delta R over delta T. So you remember I explained this one, that this is basically one of the very fundamental concept of both quantum mechanics and particle physics and quantum field theory. First we start from the finite system, then we will move our definition to the infinite system. Now here we want to define, so this is a kind of classical momentum. We want to define the momentum in relativistic cases. So what we will do, we already define, we can define one quantity, like again delta x will be square root of, this is a distance between two points in this I think already been removed. So if I want to calculate the distance between these 2 points, so it will be
x2 minus x1 square plus
so there will be time first, and then there will space part. The same thing I just write in a different way of notation. And now if I take this one, c delta t out, so it will be square root of uh, 1 minus delta x it will be like c square.
C square.
Yeah. So this quantity we define as a, so whatever this quantity we define here, and this quantity, so I can write this time, and now you can see this is something like same like this gamma. So so this is the time we will use now. Okay, so we can define one more time here, which is d tau. So this d tau we can define as dt, I can take times square root of 1 minus this delta x over delta t square c square. And this time, so if I want to just to like several times you use this word time dilation, so I just want to for a one moment I can want to just write down what you mean by dt d tau over square root of 1 minus b square over c square. So is not that something is supposed to be change the notation. Is not that something looks like this time dilation one, right?
Yeah.
So now when we define the 4 momentum, so okay, just to complete the picture, so we can write, just to take the limit of both sides, then we can write.
I have one question. One question.
Yep.
So the delta t is equal to delta tau divided by root of the upper one.
Yep.
Yeah, that one. So this 1 by root of 1 minus v square by c square is gamma, right?
Yeah, this is gamma, right? So if I just
here
write
delta
down,
t.
yeah, it will be like gamma. Yeah. So this one dt over d tau, that will be 1 by v square, so that will be gamma.
Okay. What I'm thinking about is like the dt is like our frame of reference, the inertial frame of reference. D tau is the frame of reference of the moving frame. D tau. Now when we multiply dt is equal to gamma into d tau, gamma is always greater than 1.
Gamma is greater than 1, yes.
Always gamma is greater than 1. So that means like a small change that is we are seeing in our frame of reference. The time is now like I'm trying to say like in my clock 1 minute has passed. In the other clock it should be 1 hour. Gamma into d tau. Okay, Hardan. I mean, what I'm thinking about is like, since the time is dilated in a moving frame of reference, the d tau must be larger than the dt. That's what I'm confused. That's what I'm confused about.
So this the time is dilated. The time in the frame of reference of the particle.
Yes.
Yeah.
Okay, can we say like this? So d tau is the clock that is running on the particle.
On the particle.
Right, and that clock has like 1 minute has passed in that clock. Okay, and then when I see it, so that 1 minute will be like 1 minute times gamma.
Yes.
Can we interpret it?
Yes. So okay. So according to this time, like suppose this gamma will be more than 1. So whatever this dt, it will be so this dt you get after multiplying something with d tau.
So dt is always larger than d tau.
So this is dt is all larger than d tau, right?
So dt is larger than d tau, right? dt is always larger than the d tau.
Yes. So suppose this is you multiply this quantity I just consider just for reference 2, which is larger than 1, right? And you multiply this with 3, you get 6.
No, that's okay, but I'm trying to understand the physical meaning actually.
Yeah. So
dt is always larger than d tau. So 1 minute has passed in the clock of the particle. 1 minute has passed in the clock of the particle. For me, it will be 1 minute times gamma. So I'll be seeing it longer. Is that correct? Is that how I say it?
The time is taken. Suppose like the example we were discussing in the beginning. Suppose there is one muon which is decaying. Okay, so in the moving frame, like the muon frame of reference, whatever the decay time or the time is taken to decay from muon to other particle, and when we consider that when we consider this relativistic cases, so in our frame of reference we calculate the time, we can see this particle which is decaying, the time is increased, right? So that's why we
Yeah,
was
yeah.
thinking that when the particle reached to the ground. So initially, if we just simply look into the time, the decade half time, so that was smaller. But due to the relativistic cases, when the particle reached to the ground, the time is increased, so that there's a possibility this particle can reach to the ground.
Okay, I just need to like get my head wrap around this concept. Like, so when I'm always like mixing between the clock running and the time I perceive.
No,
So
this
the
is
d tau is the clock running on the particle. Dt is the clock running in my side on the initial laboratory frame. You can think of laboratory frame.
so this is
So
my
1
rest
minute has
frame.
passed with the
This is
clock
my
of the
rest
particle.
frame.
So for me, it will be longer than 1 minute.
Yeah, so just for one time, let's clarify this one. So this is my rest frame, and in this frame, I consider my time is t. Forget this one for a second. We'll come back to this one later. So I consider time t in this frame, and this frame is moving with velocity v, which is of the order of speed of light. And then we want to calculate the same event at time t prime. So according to your thinking, which time will be larger, t or t prime? I mean, I'm just trying to understand the way you are thinking, so we can clarify, right? So
Yeah.
so this
So
is
I'm
time.
thinking like
This time is time at rest, and this t prime time in the moving frame.
Yeah. So the t will be larger.
So why do you think
The
that
time
will be
at rest will be larger.
I mean, why do you think that?
Because the t dash, that frame is moving at close to speed of light. That means the time will be dilated.
So time dilated.
So time dilated means the clock will be running slowly for that. So when I observe, so for me the time when I observe that time, my clock is running at normal speed. So I'll be looking for I'll be seeing the decay longer. Like as far as the particle is concerned, the decay would happen in 1 second, but for me the decay is happening at 10 seconds.
Yes.
Like for 10 seconds, I'm observing the decay.
Yes, that's true. That's exactly what it should happen. Like when your time will be slow, so to see, I mean, here the time will be slow, right? So when the time will be slow, that means to observe something, you need more time, right?
Yes.
So in one case, when you're talking about dilation, but actually to observe something, you need more time, because your time is not something. Your time is frozen there, but it's just the way of interpretation. That the thing already happened, so you are, because now the thing is not classical one. So when there's the particle or the clock is moving, not clock, the frame is moving in a very high, in the very large frame, then your time is, I mean, not really the clock is, it's not really happened that your clock is moving slower. It's not the case, but the phenomena you are observing, that phenomena, the time will be delayed, so you have to wait more to observe that phenomena.
Correct. I think by this way of thinking, I'm becoming clear actually. Like saying that, okay, the mu1 is actually in mu1 frame of reference, it is decaying 1 second, but I'm able to observe that for 10 seconds.
Yes.
I think that makes it very clear for me. Like I can observe for longer, even though that according to that frame it is faster, but when I observe it, I can see it for longer time.
Yes. So if you think in terms of clock, then it's very easy to mix up, because according to the definition of clock, that clock should be slower. So you need to think the clock's slower, but you have to wait more to observe something.
Correct.
So now let's define. So I think now it is clear, right?
Yeah, it's clear. Yeah, I always like, I mean, when we wrote d tau, right? I mean, I was thinking in the terms of clock. when I take things in terms of clock, it should be like yeah.
So yeah, you need to think in terms of the frame reference. So the momentum. So do you have some time constant today, or because I want to complete this Compton scattering?
No, I don't.
You don't have, right?
No, I don't have that.
Because I don't want to just going faster, because this is something fundamental one. I want that you understood, so I just going slower. So okay, so now we define the four momentum. So the first component, so again this is my 4 vector. I can use mu, but I don't like it. So I just write dx naught. So here instead of using the t, I use tau now. And then so this is my 0th component of this momentum. So the position mass time velocity, kind of like velocity, but this is the velocity in terms of d tau time frame. And
one question.
Yeah.
So the first component in a 4 vector scenario, the first component, is that time? Does it have a dimension of time, or is it just we have to think it like just one component?
Let's see.
There is no unit.
Like when I define this x, if I want to think in terms of dimension, so this is a kind of event, right? I consider define as an event. Yeah. So this component I write as a vector. So this is a position. So this supposed to be the dimension of length. So this r, if I just use this notation, so this notation we sometimes use for dimension or unit. So this is a dimension of length. So this whatever the component it will be here, it should be in the dimension of length also.
Okay.
Because that's also here, though it's a time component here, but we are trying to put in the same frame. This is position, so this is supposed to be also position. So if I just simply write time here, so it will not dimensionally correct, right? That's why we multiply c here. So velocity times time, so that will give you the length.
Yeah, meters. Yeah, m by s into s.
So this component should be always like, if I consider this x is a position, or like position for vector, so it should be the dimension of position or length. So this will be also your 0th component. This is your vector component. The same thing also we want to define here. So this is again my momentum. So this will be the dimension of momentum. So I define mass time velocity, and this is mass time velocity, but in terms of vector quantity.
And vector. Okay.
And we just define this one. We can also like make it more. So mc square. So this x naught is c time t. So if I write like this one, x naught will be c time t, and then we differentiate. So it will be b square over c square. So this d tau what I just defined, and it will be m velocity over 1 minus b square over c square. I just use the previous definition to define it here. So this is my momentum 4 vector. So either you can write like this way. Also later I will show you how we can later convert it to this energy time and velocity. So again, if you want to make some kind of Lorentz transformation here also, you can see the like this is p0 p vector, or we can p0 and p vector, and then also if you want to make a kind of Lorentz transformation between them, you can again do the same thing here also. Now let's try to look into more closer to this object. So our main, I mean, it's very common. We always know that when we write down the momentum 4 vector, we basically use write like this. It will be like energy time, sorry, not time. Sorry, it will be energy over speed of light and momentum. So let's try to understand why we write this quantity as energy over speed of light. So till now I don't use any natural ice. Every places I keep the C as it is. So we at the end of the class we make everything at C equals to 1. But for a moment we keep this as a C. So we will try to understand why we write this quantity, this zeroth component, this component as energy over C. So to do that, let's try to understand it from here. So this is m times C, and this whatever this one, if this quantity I can write like again m over C times 1 minus v square over c square 4 to the power half. I'm just talking about this one, right? So this will be square root of half, so I just take it up, so it will be minus half. And if I do this, make it expand. So if I do the expansion, so it will be, the first time will be 1, the second time will be half of this one, so you can write like in C, the first time, yeah, so and the second Taylor
series.
Yeah, it will be Taylor series. V square, and then we want m terms. C, 2c square times mc and so on. Is it correct? So the first time will be 1, so I just multiply it with nc, so it will be nc. The second time will be half of v square over c square. I multiply with c, so this will be, if I write down this term more, it will be mc plus half m v square over c. Am I correct or not? So there is, let me write down.
Yeah, you're correct. Yeah.
So this
M v square over c.
There is c square.
Yeah.
So one c will be cancelled out, so it will be half m v square c, and there will be more term. So when we are in the classical picture, so we basically consider all the above term, like not even like very high speed. The above term will be 1 over v square. Next term will be 4. So that will be already tends to 0. So we just only focusing on this one. And now look into this term, half m v square. So this is at the beginning I defined the kinetic energy, it is half m v square.
That's kinetic energy.
So I can write down this term as a kinetic energy over velocity.
Speed.
So or speed, yeah. So whatever with this quantity, so this quantity should be in the dimension of energy, because this is energy and there is speed down. So energy over c.
Speed.
Yeah. So if I just write down once again this one, so this term, it will be kinetic energy and whatever this quantity I can keep it like this. And this will be giving, so this quantity, so this quantity will be my one of the momentum 4 vector.
Gotcha. But the E term over here will be like the E term will be like E square is equal to PC square plus C square E power M square C power 4.
Yeah, let's see how we.
Is now we are depending.
Yes. So let's like if I yeah, so E square. So where I'm just trying to derive this formula once again. So this is we just get this is we know this one. So I just trying to find out how the formula came out.
Okay.
So now let's see. So this is one of my 4 vector I defined. Now if I want to get from here, so let me write it on once again for clearly what I said. So my first term will be nc over square root of 1 minus v square over c square and my second term is mv over square root of 1 minus v square over c square. Now I want to do the inner product between the same 4 vector. So this is one of the things we will use when we try to solve this relativistic kinematic problem. So what will be happen if I do the inner product this p with p itself? So this will be this term m square c square, and this will be 1 minus v square over c square. Like if you remember, I define like this way: x dot x, it will be 0th component x0 minus r dot r.
Yeah.
So if I use the same thing here, so this will be just square of this one minus m square v square 1 minus v square over c square.
Yeah.
So
Yes.
if I take this m square c square common from here, what it will be left? So this p dot p, if I take m square c square common, it will be left like 1 minus v square over c square. I just take this one out, so it will be v square over c square, and the down 1 minus v square over c square. So this quantity will give you m square c square. So see, is it correct or not? So what I did, I take this m square c square common from here. Okay, let's go one step back. It was too fast. So if I take m square c square common from here, so the first term will be 1 divided by 1 minus v square over c square.
V square c square.
And the second term will be v square c square divided by 1 minus v square over c square. Because
so you're taking m square, yeah, v square by c square. Correct. That's correct.
So now if I do like this one, m square over c square, so downward will be 1 minus v square over c square. Just do the LCM.
1 minus v square by c square. Yeah, good.
So it is the same term. So it will give you m square over c square. So because it is the same term, so I can just write like 1.
Yeah.
So see, this is something beautiful here. So you have one vector which had lot of velocity. I mean, this quantity, the individual vector, this has depending on the velocity, right? Is your component depending on the velocity? The vector component also depending on the velocity. But when you take the inner product between them, it does not depending on the velocity. It depends only on the mass term. And this is we will use several times whenever we solve some problem. So because like suppose, then can you tell me what will be the inner? Suppose you had one photon. So this is just to you have one photon, and you want to calculate. You write the 4 vector for a photon, like you had the energy term, momentum term, and you want to calculate what is the inner product of a 4 vector, and between the 2 4 vector of a photon. So let me write down.
Yeah.
So
inner product is with respect to particular quantity. I can do the inner product for energy term, or I can do inner product for the momentum term.
Yes. So if you consider one 4 vector, this is for the photon. Okay.
Yeah, photon 1.
It have some energy term, like according to definition, there will be some zeros term, and there will be some vector term.
Yeah.
Okay. And now, if I want to calculate what will be my inner product of this photon with this photon. The same inner product means inner product between the same quantity. So according to the definition, we just calculate the inner product between two 4 vector. It will be only depending on the mass, the rest mass. So this m is the rest mass and the speed of light. So if I try to use the same thing here, just what we learn, m square c square. But what we know, the photon does not have any rest mass. So this quantity will always 0. So I don't even want to know what is the 0th component of this one. Even I don't want to know what is the vector quantity or 0th quantity. According to just the calculation I did from here, it will be always true the inner product of a 4 vector with itself. Inner product is dot product with itself. So inner product of a 4 vector, it will be always mass square time velocity of light. If it is photon, it will be always 0.
So what does it physically mean? What does the inner product of a 4 vector?
So inner product for physically meaning is like you know how the dot product work. Like suppose you have a vector.
A dot product is like a projection of one vector to another vector.
Yeah, so same like thing now. Like when you go dot product, it is a 3-dimensional space because it's a vector quantity. You have 3 components. Now you are thinking about the 4th component. So you have one event, and you want to project the event, one event with itself. You are taking the projection of one event, like when I write, like now in my case I just write E for one event, the space time, the ct time r is one of the event. Now, and suppose you have other vector. Let's first try to understand what dot product means, inner product means. I can use the same time, same position. The 2 events happening at the same time at the same position.
Same time, same position.
And we want to take the not because in 3 dimensions there will be nothing like projection, right? I mean, you want to take the replica of this 4 vector with itself. That how the inner this inner product is same like the dot product of 2, like you have vector A, you take a dot product of this with itself. So this is how the this is for the scalar, and for vector we said, like I just define this vector like this way, and it will be always m square c square.
This is for the momentum term. So when you take momentum just for a completion, just for my completion's sake, what will be the inner product of like the energy? Like this is the inner product of momentum, which is m square c square.
But energy, but here when we define momentum, it is actually energy momentum. It's a tensor quantity. It, like when I define it, I'm just on the place where I was going to show you. So when I define the momentum just a few moments ago, is mc square square root of 1 minus v square over c square, and then mv square
mv square divided by root of 1 minus v square by c
square. And I just show you, just if I do this Taylor expansion of this object, it will give you the energy E by C. Yeah. So this is your energy component. So this is a 4 vector. This is a 4 momentum vector, which having the 0th component will be energy, and this one will be our momentum. So because if you see the dimension of this one, energy over C, that will be your momentum, because we know E is equal to
momentum.
So this is your momentum. So this quantity is your position, sorry, not position. This quantity is your energy over C, which is like a 0th component of your momentum 4 vector. This is your vector component of the 4 vector. Now here, what you are doing, you are like when I taking the inner product of the 4 vector with itself. So ultimately I taking the dot product of the vector with itself, and that means it is at the same point, event happening the same point. So it doesn't matter what is the momentum of this event, the inner product of this one, I mean the projection of this object with itself will be always giving me the information about the rest mass. There is the beauty of this derivation. Like I just do the mathematical calculation and I see the inner product of two 4 vector is giving, is only depending, it does not depending on the momentum, it's depending only on the rest mass of this object. I understand what is your concern about it. Just give me one moment, then I'll clarify your concern, because I understand what you are trying to say. So let me just complete what I'm trying to do this derivation, because then again I'll be lost here and there. Okay, so one thing we came to know that dot product of this one with this one is give me this quantity. So let me write down once again. Okay, so now I just show you, like if I define my vector as an energy and this is my p vector. So this is also I can write my 4 vector. So first component will be the energy one and this is the momentum vector. And if I want to just define what is the inner product of this with this, just according to my previous definition, I just define. So this will be E over C square minus P vector dot P vector. Am I correct?
Yeah.
This is just how I define the inner vector, like the zeroth component square minus the vector components dot product.
P vector, yeah.
And this will be nothing but my P square, right? Because if I take the dot product with itself, it will give me P square. So, and this quantity I just calculate, it will be like m square c square. I just calculate
c square, yeah.
And this quantity is e square over c square minus p square. So from here, what I can get. So that's what I was trying to just derive. I mean, this is the everyone know, but I just want to derive for a moment. So if I take this quantity, this square, p square plus m square c square, p square c square plus m square c to the power 4. So this is that's why I was trying to explain this 4 vector, because see, this is a definition of my 4 vector of momentum, where I define my zeroth component is mc square, which is just dominating by this, because of the relativity I have this gamma product here, and also here also have this gamma, and then when I take the
So this last term, sorry to interrupt.
Yeah.
The last term, E square is equal to P square C square plus M square C power 4. What is it called? I mean, is there a name for that particular formula?
I think it's called relativistic energy momentum relationship.
Okay.
This is what Einstein is famous for, because earlier we know that energy is converted to mass.
Is equal to mass times C square. Yeah.
Where this M was for only rest mass. And now when I consider the relativity, the velocity, relativity in the relativistic dynamics, I define my 4 vector, and from there I can calculate what is the relation between energy and momentum. It is E square equals to P square C square plus M square C to the power 4.
Gotcha. So basically, like a particle that is traveling close to the speed of light, we should use the second formula, the relativistic energy momentum relationship, not the first one.
Not the first one, because here in this case, that's a beauty of relativity. Like whenever we in case of classical one, your energy and momentum are two different physical component or physical quantity itself. Now, when it came to the relativity, then your energy and momentum, they are treating as a same, we call in bookkeeping knowledge word, it is like they are treating the same footing. That means you give the same weightage to energy and momentum. you maybe multiply with some dimension of c, because that is just to make it dimensionally correct. Otherwise, like if I just use c equals to 1 here, you can see. So if I use this unit c equals to 1, so your e squared will be p square plus m square. So your energy, momentum, and mass, they are dimensionally identical. So that's one of the beauty of this relativistic kinematics, that when we are considering the energy momentum tensor, their energy, the geoth component, and the momentum vector, which is the other 3 component, they are identical, but you need to just do some manipulation with the dimension. So you just divide it with the speed of light. So if I just
So
write,
our homework we can take like this, like, okay, derive the relativistic energy momentum relationship starting from the 4 vector momentum component. So that could be like that's a start of the derivation.
Yeah.
Okay.
So
I'm just wondering, like, how people came up with this like 4-dimensional vector, like
this is not something
where x naught is equal to ct.
Yeah, this is something is whenever they draw this one, they basically draw some. It's called Minkowski space. It's not possible to draw in 2 dimensional, but if I just take a projection of this one, so it will be look like this one. There will be a time in frame in this way, and then they draw. No, I take the position. Yeah. So I can consider one. So this is not like a 1 dimensional. It is like a 4 dimensional object. It's difficult to just project it here. So this is something what is called Minkowski space. So it's like one event happened before that. So suppose this is your. So I define this as a past. At this point, this is my present, and this is future. Let's just try to make it like a realistic way. And one event happened in this space, suppose somewhere here, which is in the past, and that is moving with time. First it reached to the present, then is so if I want to define the event here, it will be the time and position, and then it will be change, and there are many very strong theoretical argument on this one in different approach, and then you can define one other event. If you want, I can discuss in more further details. Yeah, because this is something also, there are many things about, it's called causality, which is I think one of the very interesting concept in relativity, because causality is, we will come at some point when we're talking about this kinematics, talking about this particle dynamics. So we will come this picture later, because this is, we need it, because you know, in quantum field theory or particle physics, this is something what we really need. So for a moment,
gotcha. So that is the origin for the CT.
Yeah, this is we start from the past, then it come to present, and then go to the future. So, and then also you can see the dynamics, how it's work in 4 dimensions.
Okay.
So we come back to this later, because we need it at some point, but for a moment we just so what we learned in now, let's summarize. I talk a lot, but let's summarize what we, just to complete this picture. So if I want to calculate the dot product of 4 vector with itself, that will give us m square c square, and if it is, so this is rest mass, and if I consider for photon, this will be always 0. That is actually helpful to because ultimately, if you remember, I said in the beginning we want to do this Compton scattering one. So you had photon, right? That's why I am talking all these things, because ultimately I use this concept when I try to calculate this Compton scattering wavelength shift. So if this is photon, let's take gamma. So this gamma for photon, it will be 0. And you can see how helpful this will be when you try to solve this problem using 4 vector. And also just for general one, whenever we consider photon, for photon we consider, we taking the momentum, we define it in terms of k. This is standard notation. For particle, massive particle, we use e vector as a momentum, but for photon we use k. This is a kind of notation. This is notation for photon. And if I want to define the 4 vector, the 0th component for photon, we will write omega over c. Omega is a frequency times speed and a k vector. So this k vector is a momentum vector, and this is 0th component. Do you know how this come? Why I say this as a omega over c? Because it's supposed to be like moment energy over c, right?
Yeah, omega. Yeah, omega is a 2.0.
So this is momentum, right? So probably you know this notation. I just giving you a hint. So how this one came? This omega is k over c.
K into c. No, this one. Omega is angular momentum, right?
So omega is a frequency, right? So we can, you know, omega is defined as
frequency. Okay, frequency.
2 pi f.
Yeah.
So f is my frequency, is angular frequency, basically called that. So
angular frequency. Sorry. Not angular momentum. Angular frequency.
And k is basically defined as 2 pi over lambda. So lambda is the wavelength, and this is wave number at some point. I mean, it's also defined like wave number. And c is equals to f lambda. So can we somehow able to reach from here to, and also, so this is some kind of
it's a simple algebra.
Yeah, simple algebra. Just put here and there. So whenever you consider photon, then we take this. This is a many message that usually for other particle we use momentum as a p, but for photon, because it is some special particle, we need to it's demand some special treatment. So like, you know, nowadays there are someone called gluten. People are like, what is called, they allergic to gluten. There's some food with gluten, so they just need some special treatment. Okay. Now also in the last class, so okay, this is something what we discussed in now. Now we will try to use all this concept, all this abracadabra, when we try to solve some problem on relativistic kinematics. So I want to take the just 2-minute break. I just want to make some tea and then
sure. Yeah.
Try to solve one first simple problem. Then we come back to the because Compton one is need some more information. So let's consider the same kind of problem, but in just a little bit different way. Let's consider one photon. As I mentioned, for photon I will use the notation k. So this k is the momentum vector for the photon. Suppose I am standing somewhere here, and I am having mass m. Okay, and when this photon falls, now here I am considering photon as a particle, or you can consider, just for the simplification, let's consider a particle. And after the collision, I want to calculate. So this photon come to me, I absorb this photon. So when photon coming, I absorb it. Though if it is not very high energetic, probably I am not instantly recoil or excite, but at least I will experience this energy, because if it is like a very highly dense kind of like laser beam is fall onto me, I'll feel this momentum, because the momentum should be conserved, because this has a momentum. I am at rest, so this is at rest. So this stupid guy like me is at rest, and some bunch of photon is falling on it, and then we want to calculate what will be the energy of this. So this is my initial state, and if I want to define my final state, I want to calculate. I define my mass like m prime. So let's try to solve this problem using this energy momentum 4 vector. Okay.
So the question is like the person is at rest initially, and then a high energy beam of photon is hitting with a momentum of k, capital K, and then we want to calculate the mass of the person after that itself.
After the collision.
Mass, we're trying to calculate mass, right? Not the momentum of the person.
Not sorry, not mass. So not momentum, mass. Yes. Did I say this is mass? Yes. So we want to calculate what will be this.
Yeah. Okay.
And just to simplification, let's consider this photon is coming along x-axis. So if I define my momentum vector, it will be kx, the x component of this momentum vector, and other two components will be 0. So when I write in this notation, this actually means like this way. I can define like this way: x cap kx unit vector and magnitude plus 0 plus 0. So, but this is like a shortcut notation. So this is 0th component. So I like, instead of writing on a vector format, I just write this in a shortcut. Okay, so in the now, if I want to write what will be my initial state, so initial for this photon which having so we can write we just discuss and kx, because it have only along x component, so I don't bother about other component. And now this object was at rest, so this is my 4 vector for the photon. Okay. Now for this object, it was initially at rest, so it have only rest mass. So I can write like this way: mc. Why I'm writing mc? Okay, so let first do like this way. Usually we do. We can write like mc because it will be energy over c and 0. Now we know, because just to discuss from Einstein equation of motion, not equation, Einstein energy momentum relation, E square equals to p square c square plus m square c to the power 4. Okay, and if like this object at rest, so the p will be 0. So for me now, E equals to mc square. So the zeroth component, it will be E over c. It will be like mc. So I can write like mc. And momentum is 0. So this is for this object. Now question is, what will be happening for this one? Now after when the photon hit me, so I also had my rest mass energy, so I had my 0th component like this mc over 1 square over 1 minus square by c square, and at the same time I recoil if it is high energy, so I also get some momentum. Okay, so I can write like this one object. For this case, my 0th component, it will be like define m prime, because now my mass is, I don't know, it could be m prime, but I said this will define mass because I getting some momentum. So this energy should be converted into mass somehow. M prime c over square root of 1 minus v square by c square, and m v over square root of v square by c square.
Why it is MV? Why it is not M dash V?
So M dash V. M dash V.
Okay.
So now, there is two ways you can solve the problem. One is you can do this energy momentum conservation. You know the initial energy, you know the final energy. You can make the relation between them. because energy should be conserved. So your initial energy and final energy should be conserved. When initial energy equals final energy, momentum also, your initial momentum and final momentum. You can do this just simple mathematical calculation, like this quantity plus this quantity equal to this quantity, this plus 0 is 0, this equals to this one. And now
so we are assuming that the photon is absorbed, right? Absorbed. That's why we don't have the momentum component of the photon in the final stage after collision.
Yeah, it's absorbed. Yeah, because of the absorption, this energy is converted to mass. That's why I said the mass will be different, because I did not considering the. Now this is one way. Now instead of doing that, what we can do, we can use a 4 vector. So instead of just considering this one, let's just try to understand how, like, here like 2 equation, one unknown, you can find out some solution, but you need like a lot of abracadabra calculations. So instead of doing that, what we can do, just trying to write down my 4 vector. So in my case, my 4 vector, that's like P2 initial momentum plus K. So this K is for photon, this is for this one, and this is for this object. Okay. Now what will be happen if I take the dot product P2 with P2? So P2 is your final state, your mass is m prime. So what will be P2 dot P2? So we just discussed the inner product. It's like m prime square
m
c square.
Okay. No, I mean, that's correct. I was initially assuming that it's always. Okay, I'm sorry. It's correct. Yeah, m square c square.
So it will be always true.
Yeah. For photon, like when the P2 for the photon is 0, for any other component is m square.
Yeah. So this P2 is the momentum, full momentum for this object. It is true. Now suppose I can do this one, P2 dot P2 equals to P1 prime plus K square, P1 dot P1, just I do the expansion, 2 P1K plus K square. Now see this object, this quantity,
K square 0.
It will be 0. This quantity will be m square c square.
C square.
So what is left for me to do the calculation? I just remove this one. So what I get till now, I can just take this one. So this P2 dot P2, I get m prime square c square equals to m square c square plus 2 P1K.
Yes.
Is it correct? Now what I need So now what I need to do, so what is my K? K had only I remove this one. Yeah, so my P1 was only MC and 0 because this object was at rest. Like MC is my zeroth component, this is rest, and what is my K? K was omega over C and K vector. So if I take just multiply this one, it will be only this component to contribute. So it will be CC will got cancel, it will be m omega. Because I need to calculate this one, right? So this suppose when I want to calculate like A dot B, A is one of the 4 vector.
Yeah, got it. Yeah.
So it will be x0 square, or let me write down this way. A is equals to, suppose your x1 ct1 x1. I just take one component, and B is ct2 x2. So if I calculate a dot b, this will be c
C
square
square T1 T2.
square. Sorry, yeah, you're right. T1 T2 minus x1 dot x2. If it is vector, it will be vector sign. If it's not vector, just simple multiplication. So when I want to calculate this one, 2p1k, so it will just multiply this one, this one. This is 0. This is 0th component. So this
one question, like so this one a dot b, right? But just in a generic term, it should be like plus x1 x2, right? In a generic term.
Okay. I mean,
it is not a conjugate.
No, actually, I that's why I don't want to use this covariant contravariant one. If you take the covariant contravariant, then you need to do this. But usually, like when I calculate this one, so my 0th component square minus the rest of the vector. That's scalar minus vector. That's the definition I use. Okay. Scalar quantity minus square root of vector.
Minus the vector quantity.
This is a simple one. One can take, if you want to take this p mu, then you need to define what is your covariant form, what is your quantavariant form. Then you need to think about the minus plus properly. Just I want to make it simple, so I just take this 0 square minus vector square. Okay, so what we want to do? We want to just calculate this quantity. We know this one. This is given. M was given. So if I just simply do this one, it will be m omega. So what we can get from here, m prime square c square, that is equals to m square c square plus 2. This and this c got cancel. It will be m omega. So yeah, so now what is our main target? We want to calculate m prime. So I can take divide by c square. So it is square root of
m square plus 2m omega by c
square plus 2m omega by c square. So this everything is given. So this usually this energy is supposed to be given. So you can find the frequency. You know mass, you can see, speed, so you can calculate m prime. So you can see this m prime is not exactly equals to m because you have some additional term here.
Gotcha. Yeah, agreed.
So see, this is you can solve the problem just simply using energy momentum, two formula, one for energy conservation, one for momentum conservation. But this actually help you, this 4-vector formalism. Whenever you multiply the 2 4-vector, you can take the inner product or inner product of the same 4-vector. It will always give you m square c square. That actually help you to solve a lot of problems.
Yeah.
And that we will use a lot of time when we do this calculation in case of scatter. Now when I go to the before standard model, the final state, we will try to understand many different kind of scattering thing in particle physics. I think it's also on the waves on the list of this what is called this MIT syllabus. MIT syllabus. Yeah, there was one places where they discuss about different kind of scattering, like molar scattering, Baba scattering, and so this kind of thing. When we need this for momentum formalism to understand how the calculation is going. So I will give you one simple problem. If you have pen paper, because I just want to take some tea, probably you can calculate till then. So if you remember last time you understood this one, right? This you understood this one, right?
Yeah.
So let's give you a simple problem before to go to the formulation of this Compton scattering. So you remember last time we discussing about particle and antiparticle. Then I was telling one kind of experiment. So 2 proton, they interact and get proton, and antiproton. So the question is, so this proton was at rest. You want to calculate what will be the mass of the so this is one proton, so I said proton because I had problem to differentiate proton and photon. So this is proton which is coming, and this proton this is a second proton at rest, and then you got proton, 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 antiproton. Now the question is, what will be the energy yeah, we just define the problem. Okay, so what is the energy of the incident proton to produce proton antiproton pair? Because you can see your final state there is a proton antiproton. So this is a kind of like relativistic, it's kind of realistic example. Like you had one photon at rest, so you know what is the momentum because momentum is 0, and also at rest means if you define the 4 momentum for this quantity, if you take dot product with itself, the inner product, it will be always 0. That will be one of the clue you can. So just what we learned till now, P dot P for massive object, it will be m square c square, and for photon it will be always 0. So this is one of the hint, and yeah, so you want to calculate, let's consider the energy of this proton is E, and mass, let's consider all of them as same. Let's consider mass is defined like mp. So you want to calculate what is the energy of the incident proton so that this proton antiproton pair will be generated.
Okay.
I'll just make some tea and come back.
Sure.
So I can give you some hint to solve the problem more easier way. Exactly here, you can actually introduce this concept of center of mass frame that will actually help you to solve the problem more easier way.
Okay. So, I mean, I'm going with this actually. So the P2, which is the proton at rest, the 4 vector will be, the first component will be this the proton at rest. The first component will be
E by C.
CT. So E by C.
Yes.
And then the vector component of that proton should be 0 because it is at rest. So the 4 vector component will be
you're
E by
talking
C,
about this one,
0,
right?
0,
You're
0.
talking about this one.
Yeah, that one. That is the rest.
Yeah, so in this case, your first component will be omega over C, because now here we don't talking about okay, energy. We can say like this one, but 0. Yeah, you're right. So this will be like this will be omega over C. So. Because that is raised, yeah. And in this case, you can define like E over C and having momentum K.
Hold on. The omega over C is normally used for
sorry,
photon, right? Not proton.
So my mistake. Yeah. As I said, I always make mistakes with photon and photon. So this is P. No, I don't need to use them. Then giving MP, mass of proton, MPC, and 0. And then in this case, you have to write down this, and this. So
yeah.
So I can give you.
So since all 4 are same, right? All 4 are the same.
But here it's proton, antiproton, and you have to also think how the momentum you can consider this one, because you need to think how after the collision, like this was at rest, how the particles are moving like this way and this way somehow. Because here
but momentum of all the 4 particles should be the same, right? Because the mass is the same.
Yeah, that's actually what you need to think. But this is true. The initial momentum, total initial momentum, and total final momentum should be same. That's I can tell you. I cannot tell you what will be the momentum of individual one, because that's I don't know. That's so one thing you can do. You can think the problem in other way around. You can think if another one frame, the frame should be in such a way that, you remember I talked last time about the center of mass frame. So here in your case, this is your object which is at rest, and this is the one which was coming. So this one initial momentum was 0, but this one has some momentum. So I said I can think one frame here in such a way that the final state momentum, I mean, I can think another frame in such a way that both of them are coming in opposite direction.
Okay.
So that the total moment, because I see my total moment, this one at rest, this one having momentum P.
Yeah.
But I want to think one frame in such a way that they are coming from opposite direction.
Yeah. Okay.
So that your initial momentum, whatever it will be, that will be 0, because I just thinking one frame, they're coming from opposite direction. So if your initial momentum is 0, that means according to the center of mass frame, your final momentum should be 0. Otherwise, you need to calculate the momentum for each and every one.
Okay. I see what you're saying.
So let me try.
So why the initial momentum is 0? Why the initial momentum is 0 is because in my center of moment, center of mass frame of reference. The mass is the same, but the velocity is exactly equal and opposite. So that's why the sum of momentum is 0.
Yeah, exactly. So that's the way I define my frame. I mean, as I told last time, that you can define your frame the whatever way you want. So I define in such a way that, okay, in this, though my problem is like that, this is my target is fixed, a fixed target experiment is coming, collide, produce particle. But okay, then I think okay, I can think one object, though it was rest, because ultimately what will happen? Suppose you are in the lab frame, for you this object is moving. But if you go to this frame object, the moving which is coming, if you just go to this frame, it is actually coming from the minus speed direction.
So that is coming out.
That is coming in
minus
this way.
direction. Yeah.
So that's in that way okay. But it's not really happened because it's at rest. So in the time, okay, why not to think one frame where both of them coming in opposite direction and they collide. So why this one will help you? Because this will help you to think, okay, if your initial momentum is 0 because of the center of mass frame, so your final momentum also be 0. And then only thing you need to know about the mass.
Gotcha.
So if I just try to help you to solve this problem quickly, so okay, let's keep this one. You can see this side, right? Yes.
Yeah,
so
I can see.
I define my center of mass frame. I define Cm. So my initial momentum, that's supposed to be the mass. Not initial. Let's define the final one. Let's define the final one first. So now I have four protons, right? So the mass term will be 4 mc. Momentum will be 0.
Oh, why 4 mc?
Because how we define for momentum, the first term will be rest mass mc, right?
Yeah.
That's how I define. It's supposed to be E by C. Mass is m for proton mp c square over c. So this will be mp c. Now in the final state we have 4 protons. Their mass are same.
Yeah.
And you
do we know that?
Huh? Proton is
we know that, like, so the energy is different. The momentum can be different, but
momentum
mass
can be different. Proton is proton. Their mass could not be different. Like proton will be proton.
Okay.
But when I define this center of mass frame, because of the definition of my center of mass frame, your final momentum will be 0 because your initial momentum is 0.
Yeah, got you. Okay.
So this is your final state of momentum for vector, and now your initial state of momentum. So you had energy and momentum. So that's you need to. So if I try to write down what is my initial state momentum. So in this case, the first version has some energy and mass. And momentum. Just I was thinking one thing, I can probably make it more simpler. Okay. So in this case, so I define that when I go to the center mass frame, my target and projectile. This is called projectile. So what is the coming is called projectile. So my target and projectile both are moving in the opposite direction, but it had some momentum. So individual had some momentum. So I can write down the momentum as a P. So this is my total energy, total zero component, and total momentum component.
I think about it. So this E by C plus MC. E by C plus MC. Does it refer to like both the particle or it refers to a system? E by C plus MC.
Sorry.
E by C plus MC, the zeroth component of the initial momentum. E by C plus MC. Does it refer to individual protons, or does it refer to the system?
It's referred to the individual one. No, so not individual. That refer to the system, the whole system. So the whole system I define. Wait a moment. No, it is referred to the whole system. Yes, whole system. So what I did, my target was at rest.
Right.
My initial particle, it was moving and collide. So if I just think about the initial state, my initial state is like it has some energy because the projectile had some energy. So the geoth component I can get from energy over c. That's my geoth component for the projectile. And this particle, the rest one, it have only rest mass. It does not have any momentum, right?
Yeah.
So for let me write down here. For projectile, you have energy over c and momentum p. Okay, and for target, it does not have any momentum, but it has energy. But that is because of why I write out here Pe, because this particle have both momentum and mass because it is moving. So that's why I just write E here instead of just mass. E equals to, so this will be in E over C, so it will be MC, and it was 0.
And the total momentum is P project plus P target.
Exactly. Now, so this plus this. So if I write, now you can do like this one now. So this will also be true for your center of mass frame, because though you just change your center of mass frame, but your initial state as it is. So your projectile is coming, collide, you get the final state particle. But you define the center of mass frame that way, that total momentum will be 0. So you can just simply do your P initial equals to P final. So and then you can just simply make the square of both sides. And if you sorry, yeah. So now in this case, if you do square of your final state, so that will give you 4m p square. No, 4 actually. It will be 16. Be 4mp. Yeah, 4mp square c to the power 4. No, c square. Sorry. So that will be a final state square, because it will be like p dot p. It will be m square c square. But in your case, your final state has 4 proton, so it will be 4mp its square c square. So it will be 16mp square c square. And and your initial state, if I take the square in both sides, so your initial state with this square and this square. So if I just write down this one, that will be, just for a second, I just take c equals to 1, otherwise I just carry out the c everywhere. So it will be e plus m minus p square, and that equals to 16 m square. Because I want to calculate this energy, so it will be e square plus twice e m plus m square minus p square equals 16 m square. Now we know from Einstein relation, e square equals to p square c square, but c equals to 1 plus m square. So e square minus p square, that equals to m square, right? So here I have one e square minus p square that I can put as like m square. It is just simply you can do it, but I just want to just complete it. So this quantity minus this quantity, so this is from Einstein equation. It actually m square c square,
m square,
c to the power 4, but I just put c equals to 1 for a second. So e square minus p square, that equals to m square. So this quantity minus this quantity will be m square, so that will give you m square plus 2em and plus m square, so 2m square equals to 16m square. So I can get 2em equals to 14m square. Oh no, yeah, because there is a 2 here, so if I go into 14m square, so your energy, it will be 7m.
Yeah, so some calculation.
Just some so there is a 2m square, there's 16m square, so there, if I take it that side, it will be 14, and here 2em. So if I divide it by 2, it will be 7. 14 by 2 is 7, so 7.
Yeah, 7m.
So what is the physics here? This is mathematical calculation. That's not important. But the physics here is that you collide one proton which was at rest, and your projectile coming with some energy. So though here you just create one single antiproton along with one protons, but see, just if you just think in this way, you have 2 particles and you need 4 particles. So you need supposed to be like 3m. I mean, like if I just think in terms of momentum conservation, you're supposed to have like 3m or 4m, 4 times energy just to create one. Actually 3 times energy, because this one has rest, this one has mass m, so you have 2 more extra. So you need like 3 times more mass. But actually, relativistically, you need some energy which is 7 times the mass of the protons to create one single proton with one proton.
And yeah.
So the energy of this incident proton is supposed to be very, very high, so that you can calculate, you can generate one antiproton. So later when we discuss about the concept of field, and as I last time we just introduction class, we discuss about how the particle come up when you had a field, when there is a symmetry broken. So actually there, if the proton is not there, then this antiproton is not there, your momentum would not be conserved, because 2 particles come, your momentum should be conserved. If this proton is not there, your momentum should be broken. And then just to save the momentum conservation, like last time I said, whenever there is some conservation, there is symmetry, or if there's some symmetry is broken, that means something is wrong. And like in case of like Higgs there is a symmetry, and when there's a spontaneous symmetry broken, then you generate the Higgs particle. So here also, to save the symmetry of momentum, that one more particle come up here, which is proton. But for that, you need the energy of the projectile like 7 times the mass of proton.
Wow.
So that's why, like last time you were asked one question, that why we cannot think to just to create this charm particle. If I correctly remember.
Yeah, charm. Yeah.
So you can see, just to create one proton, you need energy. Like if I just think about, because now c equals to 1, so there should be one c square term here, because otherwise it will not conservation of dimension. So you need an energy which is 7 times the mass of a protons, or the energy corresponding to protons, and that is a huge amount of energy. So this energy is really a big concern in experimental high energy physics domain. Is that it's not that you just you want to create one proton or one just simply antiproton, you just simply throw one object with the same mass. No, you need more energy. That's why they create now this LHC tunnel, which having the energy of TeV, and then they can see the Higgs and the corresponding decay. Not directly see, but the corresponding consequence they can observe, because the energy is high. So they can go into the picture and they can see what is happening there. Like this Schrodinger problem, like until you open the box, you does not know what either the cat is alive or not.
Cat is dead. Yeah.
So in the same way, if you want to understand the structure of quarks and gluons and also the fundamental one, you need that amount of energy. So using this 4 vector, why I'm doing this problem, Because this is one of the realistic problem where you can solve a kind of, suppose you want to construct your own accelerator and you want to calculate what amount of energy what amount of energy I need to throw this projectile which will hit the target and produce antiparticle. So you can calculate this one using this 4-vector formalism.
Gotcha. Okay.
Now we'll do the
I
same.
want to just for the completion's sake, I'll later take as a homework, convert this energy into joules. I want to see how much energy will be.
I also at the end also, how, as you asked me to tell you how to do this conversion. Okay, so now let's go into the last part of the talk. What I want to discuss about in the beginning, it was this Compton scattering. Now here I will finally using the more deep into this 4-vector formalism to calculate the Compton scattering. So let me just remind you what I discussed. I had one photon which having energy that consider is nu prime, is incident on an electron, and let's draw the axis of the so here is a particle, not wave but particle. Just I want to show that it's a particle of formalism, and I have one is nu prime, and here I need electron with energy. Let's define this angle with theta. So I define my vector like k. As I mentioned, for photon I will use k as my propagation vector or momentum vector. This will be like k prime. So the angle between k and k prime is theta. So let me just in the beginning let's define this one. So the unit vector dot product of this one, this will be cos theta, because this angle is theta. So dot product between vector with this vector will be cos theta. So now I will ask you to first write down the 4-vector for the incident photon. Incident photon. So it is really photon, because I had problem to pronounce this two word separately.
Momentum. So omega by c, that's the zeroth component of the photon. And then since the photon is moving, so it has a momentum. So that should be k vector.
Okay, so
that's the 4th component. Omega by c, k vector.
So this photon, the incident one, so we can write it will be, let's take now till I use this with energy, right? E of H nu. So I use this notation, and probably this one I did not explain yet, but just to completion, let's do the one just for, because I need this one here. E square equals to P square C square plus M square C to the power 4 for photon. It will be E equals to PC. So we write E equals to H nu PC. So momentum we can write it is omega. We can write H cut omega over C, and also we saw just in the previous problem also omega over C is momentum, H cut K. So I just write down this one just for reference. Is it okay? So I just do this.
Yeah, that's right. Yeah, that's right.
It will be H cut K. So this should be vector because this is a vector component. So we can write like, let's take this quantity outside just for some simplification. I can take it to be scalar quantity. So 1 and here A square going out, so it will be, so this vector k, this vector k, it will be omega over c, the amplitude with k vector. So this quantity I can write like A square omega over c k unit vector. So this is a vector quantity. So I just define this here. So if I take this quantity out, so it will be k cap. Is it clear?
Yeah.
So this is just I just use this formalism here.
Yeah.
Okay, so this is for the incident photon. Now again, just let me remind you what will be happen if I just take the dot product with this one. P not dot product, sorry, inner product with inner product. What will happen?
0. This is photon.
This will be 0. And now I want to use this energy momentum 4-vector conservation law. So your initial will be equals to the final momentum. So let me write down the whole one at once. So what will be the initial energy? It will be A squared omega over c. I take it common. So this term 1 plus k unit vector. And what about for electron? This electron was at rest, so it doesn't have momentum. So it will be it is supposed to have only energy, right?
Yeah.
MEC, and then other component is 0. And then what will be happen for the final one? If I use the same notation again for the final one, then
one second. Like, what did you write? 1 plus k vector, 1 comma k vector.
Sorry,
right?
sorry. I did. Yeah, so you're right. It should be 1 comma. Okay, and the final one.
Yeah.
What I can do here, the final one, it will be also same, but instead of k, it will be k prime.
Right, but k prime is k vector cos theta.
Yes. So
K vector cos theta.
Yeah. So yeah, the final one, it will be sorry, I need to this one. I will not use it, but I just want to show this one. And here, one thing so the frequency also be changed. So I take the frequency as a prime.
Okay.
Because this electron will recoil, so it change the energy. 1 comma k prime, and this one also had some momentum. I don't want to, because now to write down, okay, I can write down like this way. MEC, and then P of electron. Am I correct?
Yeah, this makes sense. Yeah.
So now what I do, I'll do this, I will use the formalism of the 4-vector. So I will write like this, we just remove this one. So let me just first write down P photon, the initial one, plus for the electron, that is final one, plus electron and prime. Let's take it prime. Just I want to do one thing. Okay. So let's take, just to change the notation. I'll just so this momentum I just write like P0, because this one I don't want to use it, because if I want to use this vector, now let's try to understand what I'm trying to do. I want to use so this quantity, this P, I just want to take a dot product with this itself. So because I know the energy of electron, so I don't need the momentum term. So what I will do, I will take this P0 equals to P gamma minus P gamma prime, this term with this plus PE. Am I correct?
Yes.
So now I'll take the square, dot product with this one, P0 with P0, and square of this side. It will be P square plus square of this one, P gamma minus P gamma prime plus 2 PE P gamma minus P gamma prime. So now tell me what will be this one. This will be the only, it will give the mass of electron, right? Because P0 is this one. So this will mass of electron, me c square. This is also mass of electron because this is also depending on, this is the momentum for this photon, me c square.
Correct.
Okay. And also if I expand this term also, just I want to expand this one will be P gamma square. That will be 0. Because dot product, it will be dot product also 0. Only contributing term will be minus 2 P gamma and P gamma prime.
P gamma dash.
And plus 2 PE P gamma minus 2 PE P gamma prime. Now look at here, this quantity is the same term. So only thing is remaining this thing here.
Yeah.
Let me rewrite this once again in the top. This calculation is very easy. It's nothing some rocket science, but I just wanted to do once just to show. I mean, I can do the calculation other way around, take the vector, but I just want to show this is how easy it is if I take it on this way. Okay, so what is left for me? It is, so I had one p electron, this one, so yeah, so if I just write down, I was missing something.
So 2 PE P gamma is equal to
2 P gamma prime
P gamma
is equal
plus 2 P.
So this term will be 0 if I just take in this side. So just take this side here 2. So what this P is common, so I take P here. This P is common, so it will be P
gamma minus P gamma dash.
I just keep it like this way for a moment. So this I just remove this P with this P. So this is my kind of one. Now I just want to write down the formula I write earlier. Okay. So this for PE. So PE is the momentum of this vector.
Yeah.
This electron, and it has only rest mass.
Yeah.
Okay. So if I write down, it will be me into c, me into c, and now this is the forward momentum of the photon which is incident. So let me write down the vector component itself. So I think this part I can just remove. So if I write down the MEC, it has 0, 0, 0 component, and then if I write down this one, let me just it is minus component, so h cut omega over c. One is frequency, I write omega prime minus nu. Let me write down that I'll explain because it will be just. Okay, this is the one, and the vector one will be h cut omega H cut omega over C, H cut omega over C. Sorry, I take this 2 omega C. Sorry. Let me do the calculation. So, M C then 0, 0, 0. Okay, can you tell me the 4 vector of this incident photon? This one, right? It has H omega over C, comma H omega C. So if I write H omega over C, it will be 1, comma K vector.
Correct.
And for the outgoing one, H omega prime over C into 1, comma K vector prime. Because the outgoing has a defined momentum.
Yes.
Okay.
Well, that's okay.
Yeah. So if we just put this momentum component here.
So one question.
Yeah.
So this is K caret. K cap.
K cap, yes. It's a unit vector.
Yeah. Unit vector. So both the unit vector has to be the same, right?
No, one I defined this K because this is coming on this direction, right? So this incident photon is coming along the y-x axis, but the outgoing photon is going along this direction, right?
Okay. So that's the unit vector for that direction. Okay, gotcha.
So that's why I mentioned this dot product here. Okay. So if we just put this 4 vector component here, and then I'll send you this note because just write down the formula once again here, and then finally when you calculate this one, then so ultimately you have one frequency here, another frequency here. So these two frequencies are not same, and then if you convert into wavelength, so if you just put this vector and this vector this component here and just do the product of this one each other. I'll send you this calculation because it is just mathematical one. Then what you will get H EMC into 1 minus cos theta, because this theta is coming from, because there is this vector, and these two vector. When you calculate product of these two vector, you will get a dot product of this with this, and that basically give you this theta angle here, because there is a dot product here, gamma and gamma prime. So this dot product will give you this cos theta one. So this is I'll send you this full derivation, but just for the physical point of view. Now suppose I don't do the derivation, but I want to use my intuition to calculate this one. Okay. Now this is the where that's why I told you that I want to discuss this unit at the end of this Compton scattering. Now see here, you had one photon which is incident here, and its wavelength or energy is changed because obviously it's recoiled the electron, so its energy will be changed. If energy change, the corresponding wavelength also be changed, because wavelength and frequency, they are interconnected. Yeah. So now here what will happen, let's consider these two are not collide at all. I mean, your photon is coming, the angle is 0, suppose. If your angle is 0, if your theta equals to 0, then cos theta equals to 1, right? If your cos theta equals to 1, so this term will be 0, so whole term will be 0. Then your initial wavelength and final wavelength will be identical. There will be no wavelength set. Now, instead of this theta equals to 0, if suppose this photon after collision it's make this angle. So whenever this angle will come, so this angle will make some contribution. That contribution will get from here. Now it is a wavelength. So it is a dimension of length. So we want we need a unit, or need a kind of quantity which can give me a dimension of length.
Right, right.
So let's see how we can get from here. So ultimately, can you just check what the dimension of this quantity? I just yeah. So this is your
H is equal to E by this H is a Planck constant, so the dimension of that quantity is joules second. At least the unit of the quantity is joules second. Joules is energy, so we can say it's force time.
This is the Compton wavelength.
This is Compton wavelength, yes. So what we try to understand, because that is what I just make it in other way around. So I just do this calculation, and then we calculate this quantity, and we said that the maximum, if I consider theta equals to pi by 2. If our theta equal to pi by 2, then whatever the thing we will get, so now we try to understand how this quantity is a dimension of length.
Becomes length. E is equal to h nu, or E is equal to hc by lambda.
Let me just erase this part and write down what I wanted to understand. So we find out our Compton wavelength. We will define lambda c. This Compton wavelength is h over mc. So we want to understand the dimension of this quantity. Mathematically, we found that this is something.
Yeah, E is equal to h. When you do E is equal to h, we can get a dimension of length.
How? If I consider E
so E is equal to h nu, and E is also equal to mc square. So mc square is equal to h c by lambda. H c by lambda. The nu is h c by lambda.
Yeah, yes, kind of lambda will be, yeah, h over n.
So lambda is equal to h by mc.
So so this is, I mean, this, see here, usually this kind of quantity, this h, m and c, they had a kind of usually we know that h, we discuss like it has a unit of, let me write down, yeah, it has a unit of something 1.10
joules
to the power minus 34 joule per second, right? And if you want, you can also write down in a more elaborate way. Suppose you want to write down the unit of dimension of h, this dimension of energy or dimension of frequency, as you said. So this will be energy. Energy means it will be like, if I think in kinetic energy, it will be half mv square. So it will be m square.
Hardan, it's joules second, right? Not joules per second.
Sorry, again I mistake. Last time also I did the mistake. It is joule times second. Yeah, so yeah. So I can write this one as a mv square is L square over T square, and this is 1 over T. So I can write down this one as this quantity, so it will be m L square over T. So I can write down again, it is more into like L m L over T. L m L over T. So this is dimension of length, this is dimension of mass and velocity. So whatever we can, the picture I trying to draw here, that whatever h, dimension of h, we can write down this one also as a length times mass times velocity, which is momentum. And
Momentum.
so it is this formula, like L momentum angular momentum equals to R cross P. So this quantity also you can write down a dimension of angular momentum. Let's write down this one, angular momentum. What I'm trying to say, sometimes in the future, when in the next class we will talk about the spin statistics. So in the spin statistics, whenever you're talking about the like spin half particle, or sometimes we talk about spin zero particle, then that time most of the time we use a spin half, is like we can write it half h cross. So spin is angular momentum vector at least, but still here we use the dimension of h cross, because if you do this dimension analysis, you can find out this h is also a dimension of angular momentum. That also we sometimes use. So here also, just to come back, let's complete the picture. We can do one more thing, like dimension of h equals to like dimension of r and dimension of p, because it is the dimension of angular momentum. So dimension of r is dimension of h over dimension of momentum.
Okay. So that's what we see.
And this momentum, obviously, if momentum we can write a mass time velocity, but you can take speed, c equal to speed of light. So then also you can see this quantity is a dimension of length. Now the final question, what you asked, that when in physics, actually in high energy physics, we convert our we use basically the fundamental units, we call like natural units. Then like just look into this quantity. If I put h equals to 1, c is equals to 1, then this wavelength, basically it will be 1 over mass. So dimension of length or unit, it will be of the order of 1 over mass if I consider this natural unit, h equals to 1, c equals to 1. So the concept of natural unit like it is defined in such a way that, like later when suppose let's consider one example of let's take mass or like length, like here what do we discuss, this length one. Can you write down what will be the length, unit of length in terms of this quantity? What will be the unit of this Compton wavelength in terms of h? Mass is
Joule second divided by kg meter per second square. So yeah, it's a complex one. So Joule second cube divided by kg meter.
Yes, so it is like a long complicated one, right? But one can do the thing simple, like okay, I consider h equals to keep h as a h. I consider h as a unit, right? So I don't want to change it. I just keep as it is. Now mass, we know according to Einstein equation of motion, is equals to mc square. Now, as I mentioned at the very beginning, the energy unit we will use either MeV or GeV or EV. So let's consider high energy physics, because then only we can use this convention. Let's take this is GeV unit. I want to calculate the unit of mass. And here at this point you can keep this c square, okay, but you can take this c square as a unit itself. Now this c square is itself a unit. So you can write the mass in GeV over c square.
Okay.
And even still, if you are still lazy, you can put c equals to 1. Then you can write, okay, the unit or dimension of mass is dimension of energy. So you can use the unit of mass is just simply GeV.
Okay.
And like here, if you want to come back to calculate the dimension or unit of length, so I keep for a moment h as it is. It will be GeV over c square, then c. Okay. So I put m equals to g over c square. So I can still write like this way: h GeV over c. If you want, you can use this unit also. But if you lazy like me, you can just simply put h equals to 1, c equals to 1. So it will be GeV to the power minus 1. So see, you write the unit of length in terms of energy, because energy unit is GeV. But what we are doing, we are so lazy. And also we had one thing we had, that our energy is very large, so we can use the unit of GeV. And then at this domain, we can consider c and h is 1. That's our freedom to choose. We just simply move this one, this one, then only this GeV is left. And this GeV is though it is a unit of energy, but we write in terms of length. The same thing you can do for mass, like I did here. Mass is basically GeV, because if you put c equals to 1, this quantity vanishes, so it will be like simply GeV. Though the GeV is the energy of unit, but you can write for the energy of mass also.
Okay.
Is that was your question, right? In the beginning, what?
Yeah, that was my question. Just one problem. Like, let's say that my distance is 4.1 GeV. What will be in terms of SI unit?
So actually, then you have to go back. If you need to do the back calculation.
Yeah.
So you need to go from here. Then you need to go to here, because this is your final unit of length, right?
Yeah.
So you need to start write this. You just write down the equation like this way. So you need to know, if I want to know the length, what I need h GeV over c. Like I can write like this one. So I wrote lambda.
So is it like, for example, if I say like 4.1 GeV length, which is 4.1 inverse, right?
Let's say you said 4.1 GeV to the power minus 1.
Inverse. Okay. Yeah, exactly. So now if you want to convert SI unit, so all I have to do is like multiply by H and C, which is like 6.034 by 10 minus 34.
Yeah, exactly. So what you need to do, 4.1, and then you just need to convert it into H and C. You have to multiply with this one, because you want to just convert it, just going backward. Just one step back.
So H and C multiplication is 0.197 femtometer. So 4.1 into 0.197. That's like 0.2.
I think there is this is a very, I think, popular one number. I think I wrote somewhere. Because there is a popular, when you multiply these two quantity, it will always give a kind of the order of 100 MeV over femtometer. I think there is one. Just give me a sec. I think.
Yeah, 0.197 femtometer.
Yes, I think something like that. There's a very popular formula. So one need to keep in mind. I forget easily.
So that's like 0.2.
Yeah, I just wrote down somewhere this formula. Yeah, so if you consider H over C, that will be of the order of 200 MEV femtometer. So you can
Oh,
just
MEV femtometer, okay.
you can use this as like a basic, or if you want more precise, it is more precisely 197, which I never can remember. Yeah, 197.33. So if I write 1 femtometer, your one mega electron volt, that is equals to H cut over C 197.33 femtometer inverse. So you can just use this conversion law.
Okay.
But I think usually nowadays, like whenever we solve this kind of problem, at least in high energy physics, yeah, one can do this calculation if they want. Like now, one can change the femtometer to like, okay, if I want femtometer, it will come here. So it will be femtometer. So one femtometer, that equals to 197.33 over H cut C and that is MEV. Yeah. So 1 femtometer is 10 to the power minus 15, right?
Yeah, 10 to the minus 15. Yeah, MEV inverse, right?
No, it was somewhere here. Okay. So
just MEV inverse.
Let me write down. You're right. MEV. You're right. Yes. This one time H cut over C 197.33 1 MEV. Yeah, you're right. It will be MEV inverse. So 1 femtometer is 10 to the power minus 15 meter. That is equals to 197.33 over H cut C MEV inverse. So this is just, you have to take a calculator and you have to put all this number, and then you will find the conversion. The better thing is just write a small piece of code that A is equals to this, and then you can find the conversion.
Okay. So, Hardan, can I get the notes like?
Yeah, I'll send you. Because this Compton one I did not derive fully, but I think the last two lines you just to take the term here and there.
No, the other one also, like the 4-vector calculation.
Yes, I had one complete. I think complete 2 sets of notes. So I will send you. It will be on my GitHub page. So I will upload to GitHub. Okay, so today basically I will try to do some more general one, because you can see step by step all these things we really needed, because when you do some more mathematical calculation, more deeper, though it was very basics one, whatever we discussed is very basics one, but when we start the quantum, because ultimately my idea is to doing in that way that first we do little bit of classical field theory, then just touch some scattering of this quantum field, then we do the particle, then as you said we go to the nuclear one. But to understand this part, like when we do this different scattering one, then we need this 4-vector approach, and it is really helpful when you try to solve any kind of scattering problem. Like you can do the by hand doing a lot of calculations, but this one important, this inner product of one scale vector with other is mass times c square, n square c square, that actually kind of helpful to solve problem more easily than doing like a lot of calculations. So I'll send you these two page of I think there is 2 notes, a previous class and this class, which you will on GitHub, and also there is one homework specific one. So this homework also you can if it is possible and you have time, you have no time constant, if you are able to solve. Those are mostly based on the 4 vectors, because the 4 all the problem based on 4 vectors. So you can play with the 4 vector to do this inner product to get some final state of particles.
Okay.
So if you have any question now.
Not at this point. I think we asked the questions during the lecture.
Okay. at least something is understood, right? This.
Oh yeah, no, yeah. It is much more clear. I just had to go and revise and then do some problems that are like completely.
Yeah.
I'll be completely comfortable.
Yeah. Okay, great. So next time we will meet on Tuesday.
Tuesday.
But on actually on February, March, which month it is? April, right? It is February, right? So
That was
on
February.
no, it is March, or which month it is now?
How much February?
February. Yeah. So on March, probably in mid March, I'll go for 10 days to Japan. So that time, because they had a different time zone. So that time, probably I don't know which time is suitable. We can discuss later which time is suitable for you. So because this 4 p.m. at Japan will be too late there. So we can manage the time both because I'm going for a conference, so I just need to take the time shift.
Yeah, definitely, no problem.
Okay. So I'll send the homework and we'll see you in
Thank you so much, Abha.
Okay, so if you have any questions, so we can discuss on this WISE application. If you have any, when we're starting this one, if you have any questions.
Okay. On Tuesday, should I learn more? At least we are going to work on symmetry, or we are going to continue on
symmetry.
I think
so first I'm going to go on the symmetry, because symmetry one, which is the another basic thing which I want to discuss. So next class we discuss about symmetry and also spin statistics, because that's also one thing is needed for because that is part of the standard model particle physics. So we discuss about the symmetry, different kind of symmetry, what will happen when the symmetry is broken, and what kind of physical phenomena we can observe for different symmetry broken. And then also at the end we will try to understand some of the spin statistics, because that is needed for our further discussions.